Hello, everyone, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenters, and I will go over our agenda. So with us today, we have Joydip and Giacomo. Joydip is the Product Group Manager of General Industrial and Aerospace and Defense Connectors, and Giacomo is a Design Engineer in the Aerospace and Defense Connectors Group. So today's agenda, we're going to highlight the current battery systems in the market situation. We will also showcase how Smiths Interconnect can provide a groundbreaking connectivity solution to the growing battery systems and market. And we will end up giving some insights on our solution and what the advantages it can bring. So with that, I would like to pass things over to our presenters today. So Joydeep, I'm going to pass it over to you to get us started today. Go right ahead.
Thanks, Katie. Good morning, good afternoon, good evening from whichever part of the world you're joining. We are hugely excited to have you with us. Let's get started to dive straight into the latest innovation from us with power connectors, and particularly the ways you could apply this innovation in real-world scenarios and the applications that you are working on. So, you see, today, much of the global energy system still relies on fossil fuel, especially in sectors that are like in heavy industry, mining, transportation. Batteries, you see, play a central role in the electrification or electrification at scale, if you like, right? As you can see on particularly the circular graphics on the left of your screen, battery systems sit at the heart of modern electrical architecture. They make it possible to electrify equipment like vehicles, processes that were previously largely dependent on fossil fuels. By combining, if you like, electrification with renewable energy sources such as wind and solar, we can further collectively reduce our reliance on fossil fuels while still maintaining reliability and performance. This shift directly results in products' lower emissions and supports the transition towards a more sustainable world that we all are working towards. In other words, batteries, if you really think this through, batteries simply don't just store energy. They are, if you like, they enable cleaner operations, safer working environments, lower environmental impact, and a practical pathway from today's systems that we have to tomorrow's low carbon future. And that is why battery systems are, if you really think this, they're simply not just an optional add-on. They are absolutely central or the core infrastructure within the overall structure required for energy transition. Now, the power connector is common across virtually all system architectures that you name the applications in aerospace, defense, rail, mining. Now, different applications, all of them, aerospace, defense, rail, mining, they're very different applications. They have all different duty cycles, but all of them have a shared dependency on the same fundamental interface, which is the power connector. The question we are critically asking and analyzing is the connector a weak link in this system? And let us explore that critically as engineers with some facts and figures. You see, a battery system scale in power and current. The connector becomes, therefore, a critical stress point. Let me demonstrate some of the key mechanisms that are at play with the power connector. It all starts with electrical contact resistance. Even when Using highly conductive materials, resistance exists at interface between the mating surfaces. That challenge, if you like, is compounded by limited contact area. I said, let's talk about the real world scenario. In real world, contacts don't touch uniformly. Currents don't flow, the currents basically flow through those microscopic contact spots, often known as the A spots. This means that current is naturally constricted in these very small areas. As a result, current constriction leads directly to Joule's heating. And what ultimately then happens is if you just work your way through this constriction current and therefore to the Joule's heating. Now the heat is generated precisely at those contact points where current density is highest. Over time, this heating accelerates the wear, increases the resistance further, and can ultimately lead to a connector degrading, or even worst case scenario, even failing. This is why connectors are often the root cause of reliability issues, or in many cases suboptimal issues, performance in high power battery systems. Not because somehow the system was poorly designed, but purely because, as I said, let's just throw out the mechanisms that are at play. This is purely because the physics at the interface is absolutely unforgiving. So there are active reliability drivers. The connectors are active reliability drivers. Now, addressing contact resistance, managing heat, and maximizing the effective contact area, these are absolute essentials, right? Absolute basic essentials if we want the battery systems that are not just powerful, but they are safe, durable, scalable across demanding applications, and most importantly, they do not perform sort of in a suboptimal way, because that is exactly what is happening currently with very many connectors out there in the market. So with that, before we progress, let's just take a quick snap poll with the participants. And for that, I'll pass it over to Katie. Katie, over to you.
All right. Thank you so much. So right now up on your screen, everyone, is a polling question. So the question's asking, from your experience in applications requiring high power connectors, how important is it to reduce Joule's heating and therefore power loss? So there's A, important, B, somewhat important, and C, not important. So if you could all give us your feedback, that would be much appreciated. I will leave this up on the screen for a couple seconds so that we can start to get everybody's submitted answers. All right, I see some responses coming through, so thank you everybody that's participating. I will leave this up on the screen for a couple more seconds just so we can get a higher amount of responses. Again, the A is important, B is somewhat important, and C is not important. Thank you everybody for submitting your responses. I'm going to leave this up for about 5 more seconds, and then we're going to move on to our next polling question. All right, I appreciate everyone that has participated. So we are going to pop up another polling question on the screen here. So our next question today is, for the application you work on, does it require intermittent peak current? So A is yes, regularly as part of the duty cycle. B is sometimes as part of a surge, or C is no. So I'm going to leave this one up on the screen as well for a couple seconds so we can get everybody's submitted answers. Thank you so much for participating, everybody. So again, the choices for this question are A, yes, regularly as part of the duty cycle, B, sometimes as part of a surge, or C, no. All right, I see some responses coming through. Thank you, everybody, for participating. I'll leave this one up on the screen for a couple more seconds. All right, Joydeep, I'm going to pass it back over to you if you'd like to show our results of both of these polling questions. Go right ahead.
Thanks, Katie. So let's reveal the answer. Trust me, I have not seen the results myself yet. So for the first question, from your experience in applications requiring high power connectors, how important it is to reduce joules heating and therefore power loss? Again, it's very interesting to see so many of you believe that it's important, and vast majority of you saying important, and few others saying somewhat important. Obvious, all of you basically saying it's not important is of course not the is, and therefore you see 0% for not important. Now let's see the answer with the peak current. Right. Okay. This is interesting because, of course, right, what you see here is quite a mix here. Uh, for the applications that you work on, does it require intermittent peak current? And you see quite a spread. And keep this in mind, because when we delve deep into what we're going to talk about, you will see that we will come and revisit this particular topic, because not all applications require peak current. So what we as engineers need to do a good of a job is to understand the ones that need have got a different set of characteristics from a connector standpoint than the ones that don't have a need for a peak current. So please do keep this in mind, because this is exactly what the true representation of the application is. Some of them require, some of them require as part of a surge, and some of them simply don't require it, right? So yeah, this is really good kind of snap poll to show the applications in real life. So thank you ever so much for taking the time to participate in these polls. So let's move on then to talk about a little bit more on the joules heating and the power loss, which all of you said are either very important or somewhat important. So as I said in one of the previous slides, there is a lot of things at play on the physics of the material and the connector. So let's just bring out a little bit in detail some of the core physical problems that limit connectors' performance today, and explain why they matter so much to end users. So from a pain point standpoint, right? So starting from the left, as I said, if you look on the top left, you have got the surface aspratized. Now, even as I said, highly polished contacts, surfaces, they only touch at limited number of microscopic high points when you have those standard machined contacts. And as a result, the actual current path, what happens, it gets constricted, as I mentioned, in very small regions rather than flowing uniformly. This is exactly what we said in before the snap poll, right, slide. But this is just to make it more visible to you about how big the problem is in areas of contact. Now, bear in mind, to make things bad to worse, this constriction is made worse by contaminant, films like oxides, starch, residues from operating environment. These are all around us. Now, these flames, if you like, increase the resistance of the microscopic contact points, which are known as the A points, A spots, which further limits the effective current flow. When current is forced through these small points, you create the joules heating, which then gets exacerbated by the aging of it through thermal cycling, vibration, and of course the material degradation. So all of these things are at play, right? To make what seems to be a good connector on day one to a poorly performing connector after a few years in operation. And this is what one has to be mindful of. So we are here to solve problems, right? And therefore, we have laid out few areas that we need to work on to make a difference here. So from a user perspective, these, the ones on the left, these physical mechanisms manifest for us 4 critical requirements that we want to work on. The first one is to minimize joules heating, which all of you basically said are very important or somewhat important, and therefore reduce the power loss and finally, and most importantly, to improve the overall system efficiency. The second thing that we are absolutely we worked on is the ability to deliver long duration, because some of you said, as part of your normal duty cycle, peak current is quite standard. And for those applications, how do you make sure that the ability to deliver long duration and stable peak current, not just short spikes, but sustained high current without thermal derating or reliability concern? Really important for applications that require peak current on as part of a regular duty cycles. And at the end, we will touch upon a few of those applications that regularly require peak current. The third thing that we were absolutely focused on resolving is to put forward a miniaturized connector, and that's just not on a size dimension wise a smaller connector, but most importantly, which I will touch upon, my colleague Giacomo will touch upon, is to reduce the cable size. This is really important because while still achieving a comparable and higher amperage, we need to reduce the cable size. That means increasing the current density, most importantly, without increasing the temperature. And the final thing that we kind of took upon ourselves as a challenge to solve is to demonstrate, not on day one, not on just day two, but for the product, a stable product performance across the entire product's life cycle. Far too many times you see connectors working perfectly well, brilliantly on day one and the first few months of it, but as years go by, they start degrading. And the connector must maintain through that process low resistance and thermal stability, as I said, not on just day one, but for years to come, particularly in harsh environment. So clearly, through this process between identifying the pain points and defining the criteria for success, we developed, what are the must to have fundamental problem statements that we want to solve, and therefore deliver efficiency, power density, and long-term reliability for end users. So everything that follows from here is just about how we address these root causes and not just the symptoms, if you like, right? So with that, we as a team we feel really privileged that we got a chance to work on to address some of these critical problems of physics, the pain points of customers, the users. And today, we as a team are genuinely proud to introduce the HPB series, an innovative and groundbreaking power connector. So yeah, that's the HPB series. Here, the product to make a difference to some of the real world challenges you will face in with power connectors. So now that the prelude is over, if you like, now let's delve deep into the features of the product and most importantly, the results of how well it performs. So what you see on the screen from top left is that this is rated current of 300 and 400 amperage at 1500 volts. It has got three different locking mechanisms. I will start with the most important one, which is the high voltage interlock. This is the electrical safety lock that my colleague will talk a lot more about. As I mentioned in the previous slide, very important for us is the peak current to address long, stable peak current. Miniaturization, and miniaturization just like not just by dimension. We will talk about how we have managed to achieve miniaturization, not just the connector, but also the cable. Then the locking mechanism, as I mentioned, the physical locking mechanism, we have got a primary and a secondary locking mechanism. And we will talk about how this product has been designed particularly for arduous or rugged environments. And we will talk about some of those areas from a product. But before we delve deep into the product's features, we must just remind ourselves that this product, the heart of the product is with the groundbreaking technology that we developed and introduced last year, which is the Hypertac Green Connect. The Hypertac Green Connect is a contact technology that we developed bottom up for delivering low contact resistance and using the hyperboloid technology. And this is the one that would make the difference when it comes to all those problems that we touched upon. So before we spend a lot more time on the connector, for those of you who are not conversant with the Hypertac Green Connect, let us spend a bit of time understanding what Hypertac Green Connect delivers and why it is the heart of the product that makes the main difference when it comes to addressing all those problems that we spend at the beginning 10 minutes on. So there's a lot of graph, as we as engineers love to see results, right? I will touch upon, in the interest of time, a few different aspects of Hypertac Green Connect. So what you see on the top left is a contact resistance of 8 millimeter contact rated for 300 amps. So what you see on the y-axis is the contact resistance, and on the x-axis is the number of meeting cycles. Now, before many of you jump to say, hold on, my application, we really don't require 60,000 meeting cycles. That's true. Most applications do not require 60,000 meeting cycles. However, this is one way of showing, because, we cannot spend the next 10 years working on proving the physics of how well the connector performs. This is one way of an accelerated life cycle testing of degrading the material, the interface material between the pin and the socket, and then seeing how poorly or how well or how poorly the contact resistance perform. And we did this test comparing ourselves against two of the other leading manufacturers in power connectors and using their contact technology. And what is really kind of evident from the top, the graph on the top left, is how, as the material degraded with the number of meeting cycles, how stable the contact resistance has been with the Green Connect, whereas the two other leading manufacturers, they started all very well. As I keep on saying, everything starts really well on day one, but how quickly the connector becomes good to bad to worse, right? And this is a proof of that statement, really. Now, before I look into some of the other aspects of it, right, one other thing that you must also pay attention here is a temperature rise, because I often say contact resistance and temperature rise are the two sides of the same coin. So what you clearly see is the temperature rise of the manufacturer alpha and beta, how quickly they increase in comparison to Hypertac Green Connect. Now, I mentioned about the peak current. Now, the peak current on the top right you see here is that when the same contact rated for 300 amps is, there is a 500 amps put through it, and you basically measure the time it takes for a plus 50 degrees C temperature rise, you very quickly see everything starts really well, but how quickly with manufacturer alpha and beta, the time it takes to increase plus 50 degrees C quickly kind of takes a nosedive. Why is that? It's all because of the graph on the left, which is the contact resistance. And then finally, what you're really interested in, which is the energy transmitted, you clearly see as the materials degrade, you are over time transmitting or transferring less energy than you initially thought. Why? What is happening to the rest of the energy? It's all vanishing up in thin air as heat, as Joule's hitting, as we mentioned, right? So we, through this series of tests, were able to prove at the contact only level that we were able to transfer up to 90% more energy in comparison to other leading manufacturer alpha and manufacturer beta. Now, just very quickly, before I leave this slide, I'll leave some of the numbers with you so that you can really picture how the gravity of the problem really we have got in our hands. A rise from 30 microohm to 60 microohms of contact resistance at 500 amps. This results a power loss increase from 7.5 watt to 15 watt per contact. This doubles the amount of local heat generation, right? So this is what the problem lies. So what looks like a simple heat is basically a leaky bucket where all your energy that you have got stored in your battery is leaking as you're trying to transfer from battery to the point of use. So with that, I pass it on to Giacomo, who is going to take us through some results of the product. Over to you, Giacomo.
Thank you, Joydip, for the introduction. We will now present the main electrical results obtained during product validation. The first test performed is contact resistance during product life. In the top left image is shown the configuration tested, where we have the receptacle screwed on a copper bus bar and the plug crimped on two different cable sizes. The 50 square millimeter for the 300 amps version and the 95 square millimeter for the 400 amps one. The test is performed measuring the voltage drop between the bus bar receptacle termination and the crimp area on the plug termination. We perform the test at 0 mating cycle and after the entire product life of 500 mating cycles. The main results obtained is a stable behavior of the contact resistance value during all the product life that is less than 100 micron for the 300 amps size and less than 80 micron for the 400 amps one. This limited performance drop in the connector life guarantees stable behaviors in terms of temperature increase during use, as contact resistance is the primary factor influencing connectors overheating. The second test presented is the current carrying capacity. The setup shown in the top left image is the same as before, with a change in the measuring system. Now using a thermocouple to measure the temperature increase by applying different current values. In the chart, we present the results of the 300 amp option crimped on a 50 square millimeter cable that is similar to a 0 AWG size. The graph shows two different lines. The orange one related to the 100% operating capacity at different ambient temperature, and the blue one related to the 20% rating capacity. The connector, as highlighted in the bottom right table, carries 200 amps, 280 amps at the standard ambient temperature, and close to 200 amps at an ambient temperature of 75 Celsius degrees. One last thing to add, this 300 amps connector size can also be fitted with a 70 square millimeter cable that is similar to a 2x0 AWG size cable, and this will increase the current carrying capacity. In this slide is presented the same test results, but for the 400 amps connector size, crimped on a 95 square millimeter cable. And as said before, the current carrying capacity remains stable during all the product life, with a nominal current value greater than 380 amps at the standard ambient temperature and greater than 270 amps at an ambient temperature of 75 Celsius degree. As before, this connector size can be also equipped with a 4x0 AWG size or a 120 square millimeter cable, increasing the current carrying capacity. The last test we are going to present is the peak current one that we mentioned before. The setup is the same as before, but providing the connector with a current value greater than the nominal one. This test simulates a typical operating situation when there is a demand for extra current just for a limited amount of time without exceeding in the connector overheating. Analyzing the chart, the x-axis shows the time in seconds, and in the y-axis shows the temperature difference between the connector and the ambient. The test stops when the temperature difference exceeds 55 degrees. Going to the results, the 400 amps connector crimped on a 95 square millimeter cable, that is the orange line in the graph, can carry 1000 amps for 90 seconds, while the 300 amps connector crimped on a 50 square millimeter cable, the blue one in the graph, is able to carry 500 amps for 210 seconds. These results, it's important, as mentioned before, remain stable during all the product life. In this slide, there is a product comparison between our solution and the connectors available in the market. Analyzing the table, starting from the electrical features, the first is the current capacity. Our solution enables to use the use of a smaller cable size for the same current capacity, reducing cost and, of course, the cable dimension. The second feature is the peak current, that shows the capability of carrying higher current value than the nominal one to meet the demand for extra current. For this test, as shown, there is no data for competitors. Moving to the IP rating, we offer a complete protection against dust and short-term water immersion, also in harsh environmental conditions like pollution degree free. That is something not guaranteed by competitor. Then we offer both the flammability compliance according to the UL 95 V0 and the compliance with the fire and smoke rail standard, ensuring that the connector is also suitable for the railway market. Regarding the locking system, as briefly introduced before, we offer 3 features: 2 mechanical protection against disconnection and 1 electrical safety protection. Regarding the mechanical, we offer a lever as the primary fastener and a lever locking system to prevent disengagement. While electrically, we offer the high voltage interlock loop, ensuring an additional safety system that avoids disconnection under load. The next feature is the dimension. We offer a connector with 1 housing only, allowing only one panel cutout. That is smaller respect to competitors for high nominal current sizes. The last feature is durability. We tested our connector for over 500 mating cycles as required by regulatory standards without seeing any significant drop in performance. That's all from my side. I'll hand over to Jennifer.
Thank you, Giacomo. Before we move on to the following slide, let me just elaborate a little bit more to what Giacomo said, just so that we are able to understand. Again, I go back to one of those poll questions so that we are able to kind of get some, put some color to that, those snap poll results, right? So, just to repeat on that first row about the operating current, often I have seen discussion centers around amperage, and we as engineers across working on these applications, we also need to perhaps include, in my humble opinion, the cable. What you clearly see is not just we are trying to position the product for a higher amperage, but we clearly are stating that you're able to achieve that with smaller cable diameters, which basically, as we will talk about in the next slide, will reduce your weight, reduce your overall system cost, right? So it's a significant, it's not a marginal improvement, right? This is a significant advantage for users in trying to reduce the overall system weight and cost. The second thing, as many of you said in one of the poll questions about peak current, and I come back to this because I really like the spread of the responses, because clearly not all applications require peak current. That is the nature of those applications. But what is sadly happening, being an engineer, if you like, is we see this quite often, that connectors that are meant for application that doesn't have peak current being used in applications that require peak current. So this is a clear, distinct kind of a difference that we need to understand, that there are certain connectors that were not meant to be, or that was not initially designed for peak current application, but actually when you therefore put them in peak current application, they simply don't perform as well as the application demands. So these are two things I really wanted to bring out of this Giacomo slide, to make sure that we kind of understand the nuances of from an application standpoint, right, from the connector. So let's delve a little bit then to summarize what HPB series will deliver. So looking at the product from a feature standpoint, as I mentioned, the power connector for us, the world will revolve around the Hypertac Green Connect technology, which is a premium 360-degree hyperboloid contact grip technology. It's not like your typical machined barrel, which only touches on a few points, which creates therefore the joules hitting and all those things that we touched upon in the first few opening slides. The rated current of 300 and 400 amps at 1500 volts. But as I said, what very few people will talk about is the lower contact resistance, because it's all good to say we have got high current connector, but the question is that how low is your contact resistance? Not just on day one, as I showed in one of these earlier slides. It is how low your contact resistance will be throughout the product's service life, therefore reducing the heat buildup without adversely affecting the temperature rise. Then Giacomo showed you the results on the peak current, right? The product has been designed for applications that require peak current. Peak current for not just as an intermittent surge, if you like, but for applications where peak currents is part of the duty cycle. And as a result, you see the products capable of sustaining peak current for not a few tens of seconds, but of 210 seconds for the 500 amp, and for 1000 amps up to 90 seconds, right? So the product has been designed for that sort of application, for sustaining the high current without, as I said, without thermal derating or reliability concerns. Then is the high voltage interlock, because again, another key aspect that we feel that when you're dealing with applications of high voltage, one should really be all bells and braces approach, really. So you need to have an active connector lock across all the different variants of the product. So as a result, you see this as a standard offering in our connector design. Miniaturization, and I talked about that in the previous slide with Giacomo's, the table, which clearly says miniaturization doesn't simply mean for us making the connector smaller. The question is that, can you make the connector smaller and the cable smaller at the same time? And we have managed to achieve both of them to have a smaller connector and a cable size. The next question, the next part of it is, that again, has this product been designed and tested for rugged environments? And the answer is yes, it has been designed and tested for rugged environments. And as a result, there are no kind of asterisk mark to say, oh, we are able to do IP67 for a non-rugged environment, and or something like that. We are by standard be able to offer IP67 for rugged environments. So why does this all matter to users, right? Why does these features ultimately, how does the users benefit out of it? As I said, again, to repeat myself, reduce the system cost and the weight. With HVB series, you will be able to enable smaller diameters of cable, but most importantly, without compromising on the performance of the product. Peak current, a big part of this product is around peak current. So rely on the HPB series, particularly for all of you where peak current is standard part of your duty cycle. When the performance matters most, you need something where you're able to clearly see that the product has been designed and tested for longer duration of peak current, delivering higher peak current without, as I said, without degrading, without thermal derating and any form of reliability concern. And ultimately, when you package all of this together, as I keep on saying multiple times, everything works relatively comparable performance on day one. The million-dollar question is that how well does it perform over the product's life cycle, which is in years, 5, 7, 10 years easily, if not more, for a connector of this nature. So that's the fundamental exam question that we as engineers must critically answer while choosing the right connector for the application. So let's talk a little bit about which applications would need such a rugged connector for applications that are operating in rugged environments. So on the left, you see the battery energy storage systems. Now, these can be you can find these in many different places, from as simple as in a container, if you like, parked in a perfectly city environment, to rugged environments. And we're particularly talking about the rugged environments in here, right? So these deployments are typically found in many different shape and form factors, but typically to support grids, industrial buffering, or off-grid applications. So from a technical standpoint, the key requirements are high power density. You need connectors that are able to provide you with fast, transient response and stable performance across a wide temperature range. These systems often operate at high C rates for short duration, which places strong demand on the cell's internal resistance the busbar design, and the thermal management. So quite an important application where the choice of connector becomes consequential, if you like. In the center, you see the battery-powered commuter and intercity trains that represents a duty cycle with frequent acceleration and regenerative braking systems, braking events, if you like. This results in this application. What you say is that this results in repetitive high peak current pulses, both charge and discharge. Here, the battery system must balance the power capability, cycle life, and safety, most importantly, right? While integrating with the traction inverters and complying with the various railway standards that are out there. So here, effective thermal control and robust BMS, battery management system algorithms, are critical to manage the degradation under these load profiles that are part of the duty cycle. And finally, on the right, what you see are battery electric mining fleets are among, I would say, one of the most demanding applications that I've come across. Now, over here, this is not like, one of us driving an electric car, if you like. Here, the vehicles experience sustained high loads, steep gradients, and extreme environmental stress. And if that wasn't enough, if you like, then you have got dust, vibration, humidity, and elevated ambient temperatures, right? So peak current capability directly impacts the vehicle's torque and productivity. You really don't want to be in a situation where you put your foot on the pedal and the whole thing becomes sluggish when you need the peak current the most, right? So while the system robustness and fault tolerance are in this sort of application is absolutely essential for safety in underground operations. When you look through across these three applications, now what is, across all these use cases, the common engineering challenge, as I mentioned earlier in my previous slide, is, and also Giacomo kind of showing that true result, is delivering high peak current with minimum voltage sag. And all you have to do this while maintaining thermal stability, mechanical integrity, and long-term reliability, because this sort of things drives the design choices at every level. This is not just about connectors, right? This is from the cell chemistry and the format to the way the modules architecture play out, the cooling strategy, the power electronics integration. As I said, everything comes together as a system to provide an optimal performance. And if one of those in that link becomes a weak link, or becomes a kind of a weakest link in that architecture, it just drags the entire system from an extremely well-performing optimal system to a suboptimal system. So, as I said, I'll very quickly finish by saying that ultimately electrification in rugged environment is a power-centric problem, right? This is not just an energy one and a successful solution that require tightly coupled electromechanical, thermal, and mechanical systems. So you have to really, therefore, pay close attention in selecting the components to the level of components, really. Now, with that, I will finish the HPP series, but just finish by saying in our portfolio, we have got very many other products that are capable of providing high power connectors. Do reach out to us if any one of them, the HPP series, the L series modular connector used across many applications from aerospace and defense to industrial, and the LHA series. So if any one of them are of any interest to you, do reach out to us. With that said, I hand over back to Katie for the question and answer session. Thank you, Katie.
All right. Thank you so much for that presentation, gentlemen. So we have a couple minutes to take a couple questions here. So our first one today, gentlemen, are the battery connectors available as 3 or 5 pole versions?
If I take that question to start with, if that's okay with you. So currently this is a single pole one. We have got other products that are available in 3 or 5 pole or multiple poles, but this one is for the time being only available as single pole. Yeah.
Great. Thank you so much for that. So next one here in the queue. In one sentence, what is the main problem this connector solves compared to standard high power connectors?
I'll perhaps again take this one. So as I said in one of the earlier slides, if you ask me to put this in one sentence, it is minimize Joule's heating power loss and provide long, stable peak current. I think that's how I'll summarize in one sentence. Yeah.
All right, Joydeep. And we have a time for 1 or 2 more questions today. So I'm just going to grab this one here from the queue. For a customer choosing between a 300A and 400A version, what are the key selection criteria?
I'll take it. Thank you very much for the question. The choice between the 300 amps and the 400 amps version is mainly based on the nominal current required by the application, and as a result on the cable cross-section that needs to be used. And more specifically, the 300 amps version is suitable for cables in the range of 50 to 70 square millimeter, while the 400 amps version is intended for larger cables, typically from 95 to 120 square millimeter.
Thank you so much for that response. So we've got time for one more here. How does the Hypertac Green Connect contact technology compare to the other Hypertac contacts in terms of performance?
So, yeah, no, thank you for that question. So, as I mentioned, right, this Hypertac Green Connect was designed with power connectors in mind. And as a result, what you see here is that we have therefore used the Hypertac Green Connect as a basis for not only this power connector that we are introducing today, but for all other power connectors that we have worked on and will be working on in near future. Because one of the main problem statements with power connectors is with as we talked a lot about, is with contact resistance and the Joule's heating and the power loss. Therefore, this Hypertac Green Connect addresses those problems for power applications in rugged environments. Yeah.
All right. Thank you so much for that answer. So we are at the top of the hour, gentlemen. We are going to start to wrap things up right now. So, gentlemen, thank you so much for being here.
Thank you, everyone.